Good evening for all two viewers who are not me. Welcome back. We're here at the STEM Shed, your resource for your below average tutoring needs. So today, after I think a 3-month hiatus because things got a little bit crazy with my real job that actually pays my bills, I haven't been able to focus on this as much as I wanted. But I wanted to pick back up. So you might remember from our last one that we went over this stuff here. So about the adiabatic expansions, isochoric, all that fun stuff. Isobaric. In another video before that, we had I took apart a portable air conditioning unit, which actually was very fun because I had to kind of take a guess how stuff worked. You'll see, which I have this posted on my notes in Instagram. I had to use this to guess where things were. I should have filmed it. It would have been pretty cool. But today I'm now going to go through the rest of it. About what's going on. So this is physical chemistry, thermodynamics. If you're, in physics, we'll call it thermodynamics. This is more in depth in physical chemistry, but I'm going to try and I still don't fully understand because again, thermodynamics is hard. It's weird. It takes a lot to understand it. There's a lot of math involved that I don't even fully understand. I'm trying to, so I'm working on it. So it's December, so I want to say cheer, and let's go through this. Alright, so remember we talked about the PV diagram and we had these weird things. And PV diagram is a scientist thing. It's what we like to look at because we like charts and stuff. Thing to notice about this, you got the isotherms right here. And keep an understanding that isotherms represent heat, temperature, and this is actually three-dimensional. This actually goes into the wall, or with reverse, where I believe coming out of the wall. So that's actually one thing I learned later. Now that I understand it, it makes more sense to me. You're actually kind of on a flat plane. If you're, you learn about this in your Calc 3, you'll learn about this a lot. Because this is kind of based on exact differential equations, which is about these little infinitesimal movements where you hold something and blah, blah, blah. Anyways, so what I have drawn right here is a general conception of an air conditioning unit. So this right here is kind of what you would see in an apartment unit. This will be inside of a little closet thing. You'll have an air filter down here in the bottom. And this is where air will come in. It comes in through here. It goes into this fan. The fan moves the air up, and then the gas molecules fill this void, and then touches the fan again, gets pushed up, comes out here, and it will eventually come back here and recirculate, which is also why people get sick a lot in the wintertime. Because mostly I'm referring to when you have heat. I got a little ahead of myself. But as heat goes in right here, or if you're in the wintertime right now, you have a heating coil right here. I'll draw like a little coil. We'll call this a heating coil. This is a heating coil. Heat coil. The heating coil works off of it's electrical work. Something I'm not really big on, but basically it heats up all these coils. The cooler air will go into here. It'll hit these and it'll move up, and this will not be activated. Your air conditioning unit will not be working. So, but that's what I'm not concerned about that today. So I'm going to erase that and give representation. So here's what's going on. I'm going to erase everything. So you're in your house and you have your warm air going in. So warm air goes in. It's hot out here. Let's just say it's 80 degrees or something right here. 80 degrees Fahrenheit. I'll be using Fahrenheit because if you're the two Americans who are watching this, that's probably what you're used to. So you see it's still going warm and warm. Then it'll get to this coil thing right here, and then it'll be cool. So it's cool, and it goes this way, and then it goes out, and it's cool, and comes back and recirculates, and eventually gets cool enough where the whole thing turns off. Alright, but how does it get to that point? Alright, well, this is one of the big things. This is apartment based. If you have a garage, if you have a garage, you'll have a piece that comes down like this, comes here and comes there, and back around and around. And you have your filter, say, right here, going up. Now, if you have an attic one, like I do, this will actually be turned on its side. And usually the filter will be down. Mine actually faces outside on the side of the wall because they have a little bit of a high ceiling. So, but it'll look like the garage one just on its side. Now, what matters the most is this part right here. This right here is the heart of everything. This is where the work is done. There's no work done over here. The work is done right here. All right. So, and I'm not counting the fan as necessarily the work. It does stuff, but it's not what I'm really going about right here. So you have these coils, and this is a compressor. This is the loud thing we are all used to. This is what you see outside. You'll see this right here outside your apartment. It might be down, so if you're on the bottom floor, you have to deal with hearing that noise. If you're on the top floor, you don't have to worry about it. If you're in a high rise, there are a lot of times up on the roof of the high rise, and giant ones. They actually move them over with helicopters. Really cool stuff. And if you have a house, it's usually just outside your house somewhere. Mine's actually just next to, right over here. And luckily it's not going to turn on right now because it's winter time. So, but this is where kind of hard is. This here's a compressor. The actual compressor won't look like this. I think it's actually a more cylindrical looking thing. But, you know, in physics, you can just use a piston as compress. That's what you're going to be used to. So we have this diagram here, and I have it kind of pre-drawn, color coordinated, and I already kind of label where these little processes are. And this is very simplified, and I'll go into a couple reasons why, but again, it all works in the same deal. Alright, so it's a cycle. Where do I start? I don't know. I guess since I went through this part, I'm going to start here. Alright, so I have a blue right here for being cool. So I'm just going to kind of bring it cool right here. So I'll have like a little blue arrow. The blue arrow is going to go through here. Alright, and this is where the warm air is going. We have going on here. And before I get too far, I want to remember what work is. So work is equal to the integral of pressure times the change in volume. So that's what work is equal to. But I mean, it can also be change in pressure or whatever. But that's what it is. That's what works. So keep that in mind while we go through a lot of this here. So as you saw, I was pointing out here, we just had to pick a place to start. So I'm starting right here. All right. So I got this relatively cool air coming through. Well, actually, cold air. This is actually very cold air right here coming through. But we'll get back to that later. So I'm going to start right here. So I got the green right here, and I'm just going to start right here, even though it'll be kind of a mix of the blue and green. It comes through here. It's going to go this way, this way, this way, this way, and this way into here. All right. So now I wrote this as 1 to 4. All right. So this is 1 to 4. 1 to 4. So what changes here? Does the pressure change? No, your pressure doesn't change. It's a constant. Does your volume change? Yes, it does. Now, what kind is this? Remember, this is adiabatic. So, you got the green. So, this is adiabatic. All right. Again, adiabatic from the Greek for passable. So, it's not passable. The heat's going to have to go somewhere. The temperature has to change. It can't leave the system. It's, you know, the heat went into it here, but now it's going out. So now remember, for adiabatic systems, your work is equal to your Q, your heat. So right here, what's going on here? The heat is going in. Your Q is going in. Also keep in mind which direction we're going in. We're going in this direction. All right, so Q, your heat, is going in. And no, not Q in. Alright, so your Q is going in. Heat is going in. So now, because that's why you jump from here to here, you change your heat. Alright, whoops. Alright, so that's what's going through here. So the work is, this is all happening, all the green stuff is going to happen in this area right here. Alright. So as you come down through here, it moves, and nothing's going on through here. Right now, this is, I'll call it warm. It's, let's say it's room temperature. It's probably not, but let's just say it's room temperature. It's coming down through here, and then it gets to here. So it's moving through here. It goes through here, comes down, moves through. Nothing's really changing here, even though it would happen like here. It would happen here, then it gets here. It just kind of stays. But you can almost imagine these are right next to each other. So you come to the next part, 4. So here's your 4. This is an adiabatic change. Now, adiabatic changes are based off of a differential equation. And not only that, an exact differential equation. And because they're weird, you can't have, you're actually doing 2 things at once. You're changing your pressure and your volume at once, but in a different manner. I'll have to go into that a little later on because I can't even think of a way to explain it right now. But, so when your compressor goes through here, it's going to slam the gas as right there. So it's going to slam it hard. So right here, this is what you're going through. It slams. This thing is pushing this super hot gas. Now, it's still hot gas. You compressed it hard, but it is not a liquid. Because when you did that, you've increased the Q so much that you've increased the heat that it's just going to increase the heat again, and it's going to just stay, because of the entropy, it's going to stay separated. So it's going to go through here, coming up through here. It's still hot, still really hot. Like, let's just say it's 150 degrees or something. 100. You saw in my video, it was like 112 coming out of there. But now we're here outside, all right? So let's just represent blue as air. So we got air right now. And you have this fan that's spinning. So your fan's spinning around. And it's pushing this. So you got this cool air going through these vents right here. So these are interacting together. And as it goes through here, it's going to start cooling things much in the same way we did up here, just opposite. Right? So we're entering, so the cool air is coming through here. And then it gets heated up as it goes through here. And hot air goes out into the, so let's just say this is 150 degrees Fahrenheit, and the outside air, see, the outside air is 90 degrees Fahrenheit. So this heat's going to transfer into this air, and you're done. So next up, all right, so we've got that taken care of. There's no real heat transfer. There's like a little bit, but it's not much, I think. All right, so here we're now getting orange because this cool air, or the air that's cooler than this right here, is getting cooled down, and it's going to go through here, and it'll keep cooling down, you know. And again, it's still a gas at this point. Coming down through here, coming through here. Or actually, it might be a liquid at this point. I'm not really sure. So it'll come through here, and then it's going to go into this expansion valve. All right. Now you saw in that video before where the tube went from small to wide. That expansion valve right there, you saw that it frosted on the outside from the condensation because it got so cold. So we are now at this. So we are moving, or we're at this part right here, right, where the air is being pulled through here and going out. Again, the pressure's not changing. It's just the volume's changing, because as this cools the molecules down, they slow down and the volume decreases. So it decreases through here. So that's what this is right here. Now, what's happening to Q? Q went in right here. What happens right here? Q goes out. The heat has left. So we're going to move down through here. And where this was compressing really rapidly, let me get the right marker. We move through here, it's compressing rapidly. This is going to take it out. So as it hits this expansion valve, the tube goes from skinny to wide. As that happens, the volume increases while the pressure stays the same. So, or I'm sorry, the pressure decreases also, but the volume also decreases. So we're doing 2 to 1. 2 to 1. So this goes through here, gets wider, and this is where it gets really, really cold. So this is really cold. So here it might have been, so orange, let's just say it was, you know, because the red we'll say the red was 150 degrees. We'll say the orange went down to, we'll say 95 degrees Fahrenheit. And then once it hits this and it expands, this drops down to 20 degrees Fahrenheit. And that's how this whole cycle works. So we're doing the blue part right here. So as you can see, the pressure is increasing. I'm sorry, decreasing. So is the volume. That's one of the cool things down. So that's it right there. That's all I can really think of. I can maybe ask more questions later. I promise to get into some more videos, and I'll even go into more detail of this as I learn more. I'm still learning a lot. I want to go over the Joule-Thomson effect. I believe that's what it's called, which you'll see on a bicycle pump, which also works the same way here. So I hope that was enough. So cheers to the holidays, Christmas, Hanukkah, whatever.